Okay, hello everybody. It's time to start the next session, and our speaker is Browne. He will tell us something about three-dimensional surface codes.
Thanks very much. When I was submitting my title for this talk, I gave it this slightly whimsical title. Let me update it with something slightly more accurate. So I'm going to talk about work with a motivation that's quite similar to Ted Yoder's talk yesterday, which was about transversal, universal gates on error-correcting codes. And what I'm going to show you today is that the three-dimensional surface code can be set up in a way such that we get a transversal set of universal gates. But the reason I gave the talk that title is that the 3D surface code hasn't really had much attention over the years. I mean, in Kitaev's initial construction, really 2D, 3D, 4D codes were all included. And it's been known for a long time that the 3D surface code exists. So how do we construct it? Well, very similarly to the 2D code, where we place our qubits on edges, and the X generators of the stabilizer are represented by the boundary of faces, and the Z stabilizer represented by the co-boundary of vertices. And that basically means the edges of which the vertex lies at the boundary of the edge. So this construction generalizes to whichever spatial dimension you like. And for example, in 3D, we can put qubits on faces. And then the X stabilizer will be given by the boundary of the three-dimensional cells, these cubes. So you can see that here, the 6 X operators around the faces of the cube. And then Z stabilizers will be the co-boundary of the 2 minus 1 one-dimensional objects, the edges. And of course, this also generalizes to 4D, 5D, 6D, however high you want to go. And of course, most of the attention has been on 2D codes for the obvious reason that they have extremely promising properties for experimental implementation. And we've heard a lot about that already during this workshop. I'm sure we'll hear more. So they have low-weight generators, a high threshold, and there are now well-understood paths to universal quantum computation via magic state injection and distillation. 4D surface codes, on the other hand, have received quite a bit of attention because of their self-correcting quantum memory properties and other nice features. I think we'll hear some more about 4D surface codes later in this workshop. But 3D surface codes, on the other hand, there's not very much. And I was so surprised when we started this project and started looking in the literature for what had gone before, that we couldn't find very many papers on 3D surface codes. And many papers explicitly leave them out. So this is a very nice recent paper from Barbara Terhal's group. And we've got local decoders for the 2D and the 4D toric code, 3D code excluded. And if you look at many of the papers that look at general properties of surface codes and toric codes, such as this classic topological quantum memory paper. Again, the 3D case almost gets skipped over, like it's less interesting than those other two. And maybe, in general, it is less interesting than the other two. But hopefully, in my talk today, I will convince you that it does have some nice properties which are worth further study. So here are some papers that I was able to find on 3D surface codes and the 3D toric code. Most of them are condensed matter papers looking at properties of the condensed matter models you can derive from this code. But very recently, this 3D surface codes have been studied in connection to color codes and how one can transform three-dimensional surface codes or multiple copies of the three-dimensional surface codes into color codes, and what insights and useful properties that allows us to derive. And I've highlighted this paper here by Kubitska, Yoshida, and Paslavsky. I guess all three of them are here at the workshop. Paslavsky. All three of them here at the workshop. And because this in particular was the inspiration and the motivation for the work I'm going to talk about today. So what makes it even odder, really, that the 3D surface code has had such little attention is that if you look at color codes, it's almost the other way around. And the 3D color code was introduced very shortly after the 2D case, and has this very nice property that it has a transversal non-Clifford gate that we've already heard about several times in this workshop. And over the last few years, there have been very significant advances in our understanding of these codes and new phenomena, such as single-shot error correction in the gauge color code. And this leads to robustness and high thresholds and a number of nice properties. Okay, and also the n-dimensional versions of the color codes have been fairly well studied, going to 4D, 5D, and higher D. And one nice property that these codes have in particular is that they've been shown to saturate the Brava Koenig bound, achieving with dimension D transversal gates at the dth level of the Clifford hierarchy. So is it time to revisit the 3D surface code? Well, let's see. So the Clifford hierarchy, most of you are familiar with it, but for those of you who aren't, this emerges in the study of the correction operators you need to apply in teleportation-based gates and state injection. But it can be understood with a recursive definition as the set of unitary gates that transform Pauli operators a certain way under conjugation. So the first level, we have the Pauli operators themselves. The second level, we have the Clifford group, the unitaries which map the Pauli operators to Pauli operators. And then the next level of the hierarchy, we have unitaries which will map Pauli operators to Clifford group operators, and so on up the hierarchy. And in particular, there are two families of gates which have been well studied, which represent these levels very well. And in particular, we can take roots of the Pauli Z operator, and we can find the S gate living in the Clifford group. Square root of that gate, the T gate, is then in the third level of the Clifford hierarchy. And similarly, instead of taking roots of Z, we can controlize the Z gate. So we can take the CZ gate, the control Z gate, which is up in the third level, and so on and so forth. So I call these two families of gates the S family and the CZ family after their Clifford representative. So the reason that the Clifford hierarchy has had renewed importance in the study of topological codes is the Brava Koenig theorem, which, sort of to paraphrase, shows us that with a n-dimensional topological code, so that's n spatial dimensions, the only transversal logical gates, or even more generally, the only constant depth logical gates one can construct lie in the nth level of the Clifford hierarchy. So this tells us, for example, that in 2D codes, we're not going to find transversal non-Clifford gates. And rather remarkably, the color codes have been shown to saturate this bound. So as you go up to dimension D, you'll find transversal gates in the dth level of the hierarchy. And the construction is actually very, very simple and easy to understand. So it sort of begs the question, well, what about surface codes? Do surface codes have a similar phenomenon? And this was sort of an open question for a long time, because for a long time the only the main surface code that was studied was the 2D surface code, where we know that there's a transversal C0 gate and transversal Pauli gates, but not much more. But then in this lovely paper from a few years ago, Kubitska, Yoshida, and Pataski showed that by transforming surface codes into a color code and using the fact that color codes saturate this bound, and applying a transversal gate at the dth level of the hierarchy on the color code, and then transforming back, you get a dth level of the hierarchy, a local gate on the surface code. So this sort of summarizes their method. And the gate you get, incidentally, is in the CZ family. So at the the third level of the hierarchy. That would be the CCZ. And the way they achieve their CCZ gate is first there is some, so they take d copies of the surface code. I apologize if that's not very clear to read. They transform via local unitaries. So local means sort of locally confined within the three-dimensional volume of the code. So local unitaries, they transform to a d-dimensional color code where we know there's a transversal T-gate. And then they transform back. And they show that this gives them a CCZ gate, or more generally, whichever is the dth level gate in the CZ family. So what our results in this talk represent really is refinement of that to show that not only can they achieve local realizations of a CCZ gate in a 3D surface code by transforming to color codes, we can do it natively. So the surface code on its own supports a transversal CCZ gate. And the way we're going to show this is by introducing a few nice ingredients. First, a very simple topological way of understanding how these transversal CZ family gates can be realized. Then we'll show a way of deriving the different types of three-dimensional surface codes that we can put together to make this work. And we'll see that it does not work with copies of identically defined codes. We need to go a little bit further. And we do all this transversally. There's no need to transform to the color code picture. So this is the structure of the talk. Again, if it's not very clear with the contrast, I'll start off by looking at the two-dimensional version of our argument, then go to 3D, show you some of the difficulties we face when we go to 3D and then how to overcome them. And then very briefly, towards the end of the talk, I'll start to speculate about how one could maybe use these codes now in an architecture for universal fault-tolerant quantum computing. So these last two sections are certainly work in progress, but there's certainly some immediate ideas I can share with you about how these codes could be used. Okay, so let's start with the 2D code. So this is all very familiar to everybody. I'd like to point out that in this representation of a single logical qubit, we have a 2D surface with two types of boundaries. We've got smooth boundaries and rough boundaries. And we can see that the logical X lives along a smooth boundary. It's a string from one rough boundary to the other. Logical Z lives along the rough boundary. It's a string from one smooth boundary to the other. And of course, as we know, we can deform these strings within the lattice by multiplying by elements of the stabilizer. So how do we get a transversal C0? Well, that's easy. It's a CSS code, and we know that all CSS codes have a transversal C0. Okay, so if you take two copies of a CSS code, if you just apply C0 gate pairwise between, you identify qubits of each copy of the codes, you stack the two codes on top of each other, and you apply the C0 gate pairwise, this realizes a logical C0 gate. And this works for any CSS code. So that's very nice. What other transversal gates do we have in the 2D case? Well, we've got an almost transversal Hadamard gate. If we apply the Hadamard gate globally, what does that do? That transforms X to Z and Z to X. You see we end up with our string of X operators along the top here has turned into Z operators. Our string of Z operators down the side have turned into X operators. And our stabilizer generators have switched around. And you'll see that if you look closely, you'll see that we no longer have a code of the same family. So initially, our plaquette operators were X operators, and our vertex operator were Zs. But now we've applied this Hadamard gate. This has been switched around. But this is easy to fix by just redefining our lattice, switching to a dual lattice, and now we've recovered a code with the same definition as before. But what's happened by making that change, our rough and smooth boundaries have switched around. Now we've got the rough boundary on the top and the smooth boundary down the side. So how do we fix that? Well, a very simple way, just rotate the code. And now we're back to the form of the original code. and we see that we've realized a logical Hadamard gate. Okay. So we know that CZ gate can be built from a CNOT gate and Hadamard gates. So therefore, it should be possible to find the transversal CZ gate. But the H gate was only pseudo-transversal. It had this sort of awkward rotation in. Okay. Well, how can we find a transversal CZ gate? Let's just consider two copies of the code which are slightly different. Here's our first code defined as before. The second copy of the code will define rotated. So it's rotated 90 degrees. So where we had smooth boundaries before, now we have rough boundaries and vice versa. Okay. So even though they're rotated, if you look carefully, you'll see there's a one-to-one correspondence between the qubits on this code and the qubits on this code. So we can pair up all of the qubits. So my claim is that this pair of codes has a transversal CZ and can be implemented by just pairwise implementing CZs in the code. And how am I going to show this to you? Well, there's a variety of ways you can see it. You can actually see it just by thinking about the stabilizer description of the code and thinking about how these operators transform under a transversal CZ. But there's another nice way of seeing it, which I want to talk through because it generalizes to higher dimensions. So we can think about representing our logical basis states using the CSS code construction. So in the CSS code construction, we take the linear code that defines the X part of our stabilizer group, and our logical basis states are formed as cosets of that linear code. And in particular, our logical zero state is just a superposition of terms corresponding to each element of that X code. And we can write it like this. We can start with a tensor product of zeros, and we can apply every element of the X stabilizer for our code, and this gives us the logical zero. So I want to sort of unpack my zero states so they sort of correspond with where the qubits are physically in this lattice. And this is our logical zero state, and this is our logical one. So now let's just think of one term in each superposition for each of the logical basis states of these two codes. So we've got the state 0 and the state 1. The state zeros in each case are represented by zeros everywhere. The state 1 is represented in the first code by a horizontal line of 1s, in the second code by a vertical line of 1s. So now we apply the CZ gate. But the CZ gate only acts non-trivially when both qubits are in state 1. So if we pair up these different codes, we see most of the time the CZ gate just acts trivially, because there are no pairs of 1s, right? In this case, there are no 1s at all, and in this case, there are no pairs. And only in the 1-1 state do we have any pairs. And in fact, we just have a single pair. A single pair where the vertical and the horizontal lines match up. So we see that for this term in the superposition, we get the phase that we want. When we apply the CZ transversally between the pairs, we'll just get 1 minus psi. And then you can consider all the other terms in the superposition, which are all obtained by multiplying with elements of the X stabilizer. But these are all closed loops like this, and you can convince yourself that as you add these loops, it can only ever change the number of collisions where we have simultaneously a 1 in both codes. It can only change that by an even number. So we always get an odd number of these only in the case when we started with the logical 1-1. Therefore, only the logical 1-1 picks up this minus phase, and we've implemented a CZ gate. So what did we need for this to work? It's a very simple construction. We just needed this one-to-one mapping between the qubits in the code. We needed compatible boundaries, and we needed the fact that the smooth boundary here maps to the rough boundary in this code and vice versa. And we needed the fact that the logical x's for our two codes were represented by perpendicular strings, and that these always met at a single point. OK, so now I want to generalize this to 3D. OK, so what do I need to consider? Well, let's first think about how our code is represented. I've introduced the code using the primal lattice description. So here it is, with our qubits living on faces. There's also a dual lattice description, where the qubits live on edges. And then our stabilizer generators are represented like this. And the logical X operator is a membrane in this code. The logical Z operator is a string. So this is one of the unusual features of the 3D code. If you're used to 4D or 2D code, it has different dimensionalities of the two different logical operators, x and z. Okay, so what do the boundaries look like? Well, we have a cylindrical structure here with two smooth boundaries at the top and the bottom, and a cylindrical rough boundary going all around the edge. And again, you can think of the case where you've pushed the logical operators to the edge of the code. So the logical x is sitting on the smooth boundary at the top, and the rough boundaries are defined by all of the possible z strings around the edge. So the rough boundaries are defined by a net of edges on the dual lattice of the code. So now, well, let's try the same construction. Let's take 3 copies of the code. Let's orient them at 90 degrees to each other. Again, these 3 planes, these membranes of logical x will only meet at a point, and it should all work. That's all we have to do. Unfortunately, there's a problem. If we just take our code and naively rotate it 90 degrees and try and fit it back together, what you find is, well, the qubits don't match up. This cubic structure does not have the symmetry we need. And you can see it very clearly just by looking at a visualization of the smooth and rough surfaces. Okay, so the rough surface is much more denser in qubits than the smooth surface, and you're not going to get them to match up. So what do we need to fix this? Well, we need to find codes such that the smooth boundary of one code coincides with rough boundaries in the other 2 codes. And we need this property to be satisfied by all 3 codes. Okay, how are we going to find this? So you can see it's quite complicated trying to do this. We want to define codes that are all defined with respect to the same qubits, but our qubits are defined on faces and edges. So we want to find lots of different lattices that somehow all coincide in their faces and edges. It's all rather complicated. So let's take inspiration from the color codes and place our qubits on the vertices and see what happens. So this is a process known as rectification in the literature, when one takes a lattice and places vertices on edges or on faces. And sure enough, when you do this to the cubic lattice, the cube turns into an octahedron, and the lattice you get is called a rectified cubic honeycomb. So I've just taken my lattice, and I'm now going to describe it, rather than describing it by these cubes, I'm describing it by octahedra. So what does this thing look like? Well, here's a 3D visualization of it. And you can see this lattice is made of a combination of octahedra and cube octahedra. 2 octahedra and 4 cube octahedra meet at every vertex. And the qubits are now living on the vertices. So how are our stabilizer generators described in this new language? Well, we can associate our X stabilizer generators with the vertices around an octahedral cell, whereas our Z stabilizer generators are now associated with the square faces between pairs of cube octahedra. Now, we notice that this lattice is actually 3 colorable. We can color the red octahedra, the octahedra red, and we can color the cube octahedra green and yellow, such that no 2 adjacent cells have the same color. And when we do that, we notice that this has a nice interpretation in terms of colors. So our X stabilizer generators are defined by the red cells. The Z stabilizer generators are defined by the faces between yellow and green cells. And we can, of course, abstract this and just say that X stabilizer generators are defined by cells of one color, and Z stabilizer generators are the faces between the cells of the other 2 colors. And the fact that these 2 things share a common edge, and an edge has 2 qubits on it, means that these generators will commute with one another. So when we do that, we get 3 different codes, and this is what they look like. We have 2 codes defined by our cube octahedra, and they have X stabilizer generators that look like this, and the Z stabilizer generators, it's hard to see here, but they're defined by triangular faces on the cube octahedra. And essentially half of the triangular faces on the octahedra are adjacent to yellow cube octahedra, and the other half are adjacent to green octahedra. So those are the sets that are used in each of the 2 codes. So now that's very promising. We've got 3 codes. Can we get their boundaries to satisfy this? Okay, well, let's have a look. In order to identify the boundaries in question, of course, we need to know what are the boundaries that we want in these codes. So we want to define, again, a primal boundary, a smooth boundary, and a rough boundary for these new codes. How do we do that? Well, we need to move back to the original Kitaev picture. And so now, starting from our cube octahedron, we map vertices to faces, and we get a dodecahedron. This is the rhombic dodecahedron. And that's one of the few three-dimensional regular solids which tiles three-dimensional space. So they tessellate into a lattice. And you can then just define the 3D surface code on this lattice in the standard way. I know that some of you prefer to work in the dual picture. So this is what this lattice looks like in the dual picture. It's, I think the name of it's gone off the bottom of the screen, but I think it's just called a tetrahedral octahedral lattice because it's made of tetrahedra and octahedra. OK. So now we just need to check that our edges work out. And we need to do that for each pair of codes. So I'm just going to show you one example. Unfortunately, it's really faded out on the picture, but what you should be able to see here is our dodecahedron face. And inside it, I have put, you can't really see it here, but this represents a primal and a dual cell on the cubic code. Okay, so our dual lattice on the cubic code is just another cubic code shifted by half a cell. When we put the dodecahedral structure on top of the dual lattice structure of the cubic code, you see they fit perfectly inside of one another. And sure enough, just as we needed, the edges of this dual cube lie precisely on the faces of the dodecahedron. So that means the smooth boundary in the dodecahedral code is corresponding with the rough boundary in the cubic code. And we can make the same analysis for the other pairings, and we find the same thing. So we can construct a code of the structure we need. And this is what it looks like. So most of these graphics have been generated by me in Mathematica. Unfortunately, I didn't quite have the patience and the time to generate a full 3D rendering of the lattice structure that we end up with. So I've made a net. So this is a net. You can print this out at home and build your own little shapes. It's called a parallelepiped. It's a word that I hadn't used since school, but it's a three-dimensional structure with parallelograms as its sides. And you see we have two square sides and two parallelogram sides. The parallelogram sides are basically obtained by slicing through this lattice along the triangular faces of the cube octahedra. Okay? So this is a visualization of that shape. And sure enough, when you crunch the numbers and you go through the analysis, you find that this supports a transversal CCZ. We take 3 copies of each type of code, stack them on top of one another, and we apply CCZ gates between all triples at a point. And we've managed to reproduce precisely the structure that we wanted, and one can prove that indeed we get a transversal CCZ with these 3 codes. I should say that my student, Mike Vasmer, who's my collaborator on this project, has a poster at this workshop, and he'll go through more details of that proof in the poster. So before I move on, I want to now compare this to the result from Kubitska et al. They had this construction mapping to the color codes and then mapping back to the surface code. So can we understand this construction in the same picture? Well, yes, we can, using a nice trick from a paper from last year by Ben Krieger and Barbara et al. So what they showed was if you take 2 2D surface codes oriented at 90 degrees to one another, such as the 2 codes we had with our transversal CZ gate, and you concatenate those 2 codes with the 422 code, which means you take every pair in the stack, every pair of qubits, you concatenate into this 4-qubit code. If you do that, you get a color code. And this is the picture of the color code that you get. So can we do the same thing with our codes? Yes, we can. We take our 3 codes, we concatenate them now with the 832 code, and this is the color code we get. So we recover the color code on a Canty-truncated cubic honeycomb. Okay? And what's happened is that basically each one of these codes has donated, if you like, the X stabilizers corresponding to one of the colors in the color code, and also the different faces that you required. The 4th color, so we've gone from a 3-colored lattice to a 4-colored lattice. The 4th color stabilizers came from the 832 code, which looks like a cube. So this is the 832 code. So Earl Campbell has a nice blog post from where I stole these images. all about this code. It's a very interesting code because I think it's the smallest code we know that has a transversal non-Clifford gate. And what's that transversal non-Clifford gate? Well, this code encodes three logical qubits within it. They're encoded like this. I mean, it's a color code, so we can interpret the logical operators with these membrane operators, tiny membranes on this cube, and string operators. And if you take this code and you apply the T-gate and T-dagger transversally in the right way, this implements a logical CCZ. So we can understand precisely what's happening here. This concatenates with this code to give us the 3D color code. And because this code has this transversal construction where transversal T gives you the logical CCZ, that maps through the CCZ, which then gets applied transversally to these codes. So it all holds together very nicely. Okay, so now briefly, before I finish, I want to talk a little bit about, now we've found these codes with a transversal CCZ, can we use them for universal quantum computing? Well, what do we need? Well, we've already seen a gate set in Ted Yoder's talk yesterday that does the job we need. If we take the ability to implement Z gates, CZ gates, and CCZ gates, and X and Z measurements, and that's all the ingredients of universal quantum computing. And again, we achieve the Hadamard gate just by using our CZ gate, using our X measurements to prepare plus states and to measure, and applying a conditional Z correction based on the outcome here. So our CZ gate gives us the Hadamard, and we know that Hadamard and CCZ are a universal set. So how might this work in practice? Well, if we think of our stacks of codes, each defined by a different color, we've seen that these codes have a transversal CCZ. We can also achieve a transversal CZ gate between any pair of those colors, for example, by preparing one of the other colors in the one state. So, of course, the one state will convert a CCZ into a CZ operation. We know how to get the Hadamard gate via this teleportation. What this will do is these two qubits will have to be different colors. So we'll get a Hadamard gate, which also changes color. It teleports from one color to the other. But of course, we can apply the Hadamard gate twice. That gives us the identity operation, and that allows us to change color twice. But if we change color twice within the choice of 3, that means we can swap our qubit between any two colors as we wish. Then, as we've seen many times in this workshop already, we could take multiple stacks, multiple codes, and we can connect them with lattice surgery. So we can perform lattice surgery, for example, between the faces of our cubes, and that will realize an X tensor X measurement. An X tensor X measurement is all we need to do qubit transfer from one qubit to another. So we can move our qubits around from one stack to the other using this transfer. We could, I should say, I mean, this is a transfer which, this is not a swap gate. This requires the second qubit to be prepared in a blank 0 state. So in order to move our qubits around without them colliding with one another, we'd need to use a full 3-dimensional structure, but that's certainly something that could be worked out, and we might see a similar sort of structure to some of the other talks we've seen during this workshop. Or we could consider hybrid 2D, 3D constructions. So for example, this has been proposed by Hector for color codes. We've also heard other talks using hybrid 2D and 3D codes. We can again use lattice surgery to transfer the information between the 3D and the 2D case, because we can perform lattice surgery and Z parity measurements between the string-like Z operators on our 2D code and the string-like Z operators on our 3D code. So how well will this code work? Well, until a few weeks ago, when this paper appeared on the archive, I was not aware of any work that had been done to identify any sort of error thresholds for the cubic 3D code. But that work had been done, and the authors of this paper were kind enough to translate the results in those papers into language that quantum information people can understand in the introduction to their paper. So from that, I learned that the optimal quantum error correction threshold for the cubic surface code for the 3D surface code on a cubic lattice is about 3%, which is reasonably high. So 3%, that's for the string-like errors, which will have a lower threshold. So that's the threshold we want to talk about. For comparison, you see that's a factor of 3 below the equivalent threshold for the 2D code, and it's higher than for the 3D color code, but it's sort of a similar order of magnitude. And this result was the main result of this paper. They, for the first time, computed an optimal threshold for the 3D color code. So you see it's slightly higher than that. Now, for the dodecahedral 3D code, of course, no one studied that, but we have reason to think that it will perform worse than the cubic code because the stabilizer generators have higher weight. But we don't know, and this would be an interesting thing for future investigation to find out what sort of performance hit you get by switching to the dodecahedral code. So to sort of summarize our 3D surface code versus the color code, I mean, should we now abandon the color codes and switch to the 3D surface codes instead? Well, this sort of summarizes what we know. I've put in bold sort of the cases where one or the other is winning. And we have possibly a higher threshold in the 3D surface codes. We don't yet know what the threshold will look like for the dodecahedral case. It could be worse. The 3D color code, of course, has the gauge code construction, which brings with it a huge number of advantages, in particular single-shot error correction, which really does remarkable things and gives you significant resilience to measurement error. So from that point of view, the 3D color code wins because we don't have a similar construction for the 2D, for the 3D surface code. Also, this is almost not really a disadvantage, but of course we get our transversal gates for the color code on a single copy of the color code, whereas for the surface code we require stacks. But as we've just seen through the code concatenation construction, the stack of 3 surface codes is in some sense a simpler object than the single color code. So in some sense, although we've got a stack here, this is still a simpler object than this one. So there I'd say they were probably even. And we have this advantage that these are directly compatible with 2D surface codes, although we've seen talks today where we've seen that you can also use lattice surgery to connect color codes and surface codes, so perhaps that advantage is a weaker one. Nevertheless, it's nice that the 2D surface codes and the 3D surface codes can be combined in such a simple way. So let me conclude with some open questions. So I've already mentioned that it's an open question how well this code performs, and that's a key question that needs to be answered to know whether we should take this seriously as a potential architecture for universal quantum computing. In particular, we want to see how well does this perform for implementing non-Clifford gates compared to magic state distillation architectures. And as we've seen this morning, magic state distillation is making big advantages, and this is a hard race to win. But nevertheless, it's rather compelling that in these codes here, we can achieve universal gates without any distillation at all. So I've shown you a specific example of a family of 3 codes which have the transversal CCZ. But can we construct a general theory? I mean, is there something special about the lattice we've chosen? Probably not. So can we show that this is a generic construction? Can we generalize it to higher dimensions, in particular 4D? I mean, we should be able to. And there one would have a transversal CCCZ gate for the 4D toric code, which could have some very interesting properties. And indeed, there may be some applications of the mapping between lattices that we've developed. I mean, the fact that you can sit the dodecahedral lattice on top of the cubic lattice is not something that I would have expected. And maybe that in its own has further applications. Of course, having now seen Ted Yoder's talk yesterday, I'm naturally intrigued whether his results have any relation with our results. Can we map the Bacon-Shaw code CCZ construction into our construction and vice versa? Are they directly related? And what would be very nice would be if we could bring some of the advantages of the 3D gauge color code to 3D surface codes, other ways of trying to bridge the gap between gauge color codes and surface codes in the same way as we've now got a very good understanding of the mapping from stabilizer color codes and surface codes. And finally, I should point out that just a week and a half ago, a paper appeared on the arXiv which also presented a construction for the transversal CCZ in stacked 3D surface codes. So this is an alternative approach to this question, which uses completely different techniques using a quasi-particle construction. And it'd be very interesting to compare these two approaches and see how they relate to one another and how one can learn from the other. Okay, so I hope that I've shown you that the 3D surface code should not be written off. It has some interesting properties. And so perhaps this ugly duckling does have some scope for promotion to swan status. Thanks very much for listening. For more details, have a look at Mike's poster during the poster session. Thanks very much for listening.
Okay, questions for them?